So I don't know what about you, but I'm exhausted. I can barely remember my name, so I thought that I should start with a brief reminder of what we talked about a day ago. So we're talking about irregularities of uniform distribution. Uniform distribution is the famous theorem that says that n alpha mod 1 visits every interval at the right frequency. Irregularities of uniform distribution is the phenomena that the error term is not evenly spaced around zero. Okay, and we discussed last time three forms of irregularities of uniform distribution. The first and most dramatic is what I call the sign bias. So this is the situation when the error term always has the same sign. And Ralston and Bosher-Nitzan characterize the alphas for which this happens. For example, this happens for square root of 2. Okay? And then we talked about two other forms of bias, global bias and local bias. So global bias is a phenomenon first discovered by Joseph Beck. And he realized that there are some alphas such that if you look at the histogram of the first n values of the error term, and you draw a bar chart, then if you look from far away, it looks like a Gaussian, except that for some alphas, the Gaussian has a drift. Okay? The center is some number an, which is not at all negligible compared to the standard deviation. Okay? This, for example, happens for square root of 5. The third form of bias is a scenario where when you look at the countable family of values that the error term takes, some appear more frequently than others. Okay? So in the case of the interval 0, 1/2, which is the only case I'm going to talk about in this mini course, the values of the error term are always half integers. Okay? And what happens in a situation of local bias is that if you compare the frequency of times the error term is equal to 1/2 integer, and you compare it to the frequency of times the error term is equal to another half integer, the ratio does not necessarily tend to 1. Okay? We even discussed the possibility of having exponential bias, where the ratio of frequencies of attaining two different values is asymptotically the exponent of a constant times their difference. So you could even have exponential bias for some angles alpha. And the question is, for example, this happens for square root of 7. Okay? Neither of these happens for square root of 3. We discussed this last time. So now the question is to understand for which alphas do you have these features and for which alphas you do not. And I stated three theorems. The first one is by Bosher-Nitzan and Ralston. It's a criterion in terms of the regular continued fraction expansion of alpha that tells you for which alphas you have this situation that the error is always non-negative. And then I stated two other theorems, which are the theorems I'm going to focus on, which characterize the alphas for which you have global bias, drift in the histogram of values, and local bias, preference of one value to other. And the criteria are both in terms of the asymptotic growth of a certain sum. So here are the sums. So what's written here? So let me remind you that everything here is in terms of, believe it or not, the even continued fraction expansion. So you have to take alpha, and then you have to form 2 alpha minus 1, expand it to the even continued fraction expansion. This is an infinite continued fraction expansion where the digits are all even. And such an expansion always exists, although of course the digits may be negative. And the characterizations of the alphas for which you have drift is in terms of this growth condition. You look at the sum of the jumps of the sign at odd places, and if this grows not like little over square root of n, then you will have drift. And local bias is again a growth condition on this sum, except that now you have to look at growth of the order of n, not of square root of n. Okay? And if you look at these two criteria, you can immediately see that it's actually very, very easy to write down irrationals for which you have local bias or global bias. You just choose the signs of the digits of your even continued fraction expansion in a way that gives you the required growth. Okay, so these are the results. And what we're going to do today, and not tomorrow, the day after tomorrow, is discuss some ideas of the proof. Okay? And what I would like to do today is try and explain to you why does the even continued fraction expansion, why is it relevant here? And maybe I will also be able to give you a hint where this growth condition appear, but and maybe not. Maybe this will have to wait for the next lecture. I don't know. We'll see. Any questions up to this point? Okay. Now, another thing that we discussed last time was a reduction of these problems to a problem in dynamical systems. And the idea was to rewrite this local discrepancy function, dn alpha, rewrite it in terms of the orbit of a certain dynamical system. So let me again remind you what it is. So we look at the cylinder map. So this is a skew product. T alpha xt is x plus alpha, t plus 2 times the indicator of our interval minus 1. So this is a map on the torus cross z, and I remind you that the two basic identities, if you iterate this map on the initial condition 0, 0, then what pops up at the second coordinate is 2 times this local discrepancy function. And if you want to study histograms, you need to count how many times you get a certain value, then you can write this in terms of Birkhoff sum. So this quantity is also very important for us. This is the quantity that appears when you look at the histogram. So this is this Birkhoff sum. Okay, these are just obvious identities, just a direct calculation. So now, the real question that we need to understand is, for example, if we want to look at the ratio of the frequencies that the discrepancy attains two different values, basically we have to look at the asymptotic behavior of ratios of two Birkhoff sums like this. And when you examine this problem, you immediately see that if your point is generic, in the sense of the ratio ergodic theorem, for the cylinder map and the Lebesgue measure, then there is no local bias. On the other hand, if the point is generic for one of the other infinite ergodic invariant radon measures of this skew product, and such measures exist, then you will get angles for which you have exponential bias, for which the ratio of the number of times you get the value eta 1 and the number of times you get the value eta 2 will in fact be proportional to the exponent of a constant times the difference between eta 1 and eta 2. So the question is, when is the initial condition, 0, 0, generic, in the sense that it satisfies the ratio ergodic theorem for all continuous functions with compact support, for one of the ergodic invariant infinite radon measures of T alpha. Okay, so this is the question. We described these measures last time. It's a one parameter family. Okay, if you are generic for the Haar measure, then the limit will always be 1, and there is no local bias. If it's not generic for the Haar measure, then we will have local bias. If we are generic for one of the other measures, mu c, then we will have exponential bias. We discussed this last time. Okay, so this is where we are. And now I want to make a statement that is both extremely trivial and also extremely deep, okay, at the same time. And the statement is this: the problem of calculating the generic points of a map is equivalent to the problem of calculating the generic points for the constant suspension of the map. You agree with this, right? So you have a map, x goes to T alpha of xa. Now let's build the constant suspension. So it's a flow. Basically you flow at constant speed, unit speed, until you hit the roof. Then you disappear. You re-emerge at Tx and you continue in this way. Okay, so clearly you can pass from the Birkhoff sums of the map to the Birkhoff integrals of the flow and vice versa, and the two problems are equally difficult. So this is a complete triviality. The reason that this statement is also very deep is that it came to me as a complete surprise. I learned of this from Artur Avila, that the constant suspension of the cylinder map has a beautiful geometric description with many, many symmetries. And it turns out to be much easier to work with the constant suspension than with the map itself. In particular, it will be more amenable to renormalization construction. So let me explain this to you. So here is a fact. Due to Pat Hooper, Pascal Hubert, and Barak Weiss, the constant suspension of T alpha is naturally conjugate to the linear flow with constant velocity beta 1. Beta is this beta, 2 alpha minus 1. Okay? On the infinite staircase, on the staircase. Infinite staircase. So what is the infinite staircase? You start with a rectangle which has these dimensions, and then you stack it on top of each other infinitely many times, up and down. So you get something like this. And you declare opposite sides to be identified by translation. So opposite sides identified in pairs. Identified in pairs. So this is identified with this is identified with this, and so on. Okay? So we are interested in a particular initial condition. And this particular initial condition corresponds to, let's say, this corner. Okay, so this is omega naught. So 0, 0, in this conjugacy, 0, 0 is identified with omega naught, this point. Okay? So now what is the linear flow? The linear flow says you just move at constant speed. It's constant velocity given by this vector. So you start from this point, then you start to move at this constant speed. Then this side is identified with this side, so you reappear here. This is identified with this, you reappear here, and so on. And then, I don't know, maybe you understand. Okay, you just move at constant velocity subject to these identifications. Now, where is the cylinder map hidden in this picture? You have to take the union of the top sides and use it as a Poincare section. Because the y coordinate moves at constant speed 1, the height function is 1. And when you do the calculation, you see that what happens is that, okay, this is an interval of length 2 instead of length 1, but that's the only difference. Half of it moves up, half of it moves down. It's very similar to the cylinder map, and in fact, there is a conjugacy that you can write down that realizes the Poincaré map with this Poincaré section with the cylinder map. Okay? So now, if we, so therefore, I'm sorry.
This is miracle of this map, or there is more general theory?
There is an uglier surface that appears if it's instead of 1/2, it's P/Q. Irrationals is completely outside of the scope of this method. Beta is 2 alpha minus 1. Okay, so therefore, if you are interested in understanding the values of this of the error term, then you have the following identity. Let's write it like this. So this is, well, we have a representation as a Birkhoff sum for the Poincaré map, but the roof function is 1. So this is going to be, okay, now I'm going to use a notation and I will explain it. Okay, so the phi beta, that's my notation for the linear flow. And what is this z? I have this surface, this staircase, I can number the stairs, okay? So I'll call this stair 0, and this one 1, and this one 2, and this one -1. So this is the value of z, okay? So z is going to be -1 on this rectangle, it's going to be 0 here, and so on. That's the z coordinate, okay? So why do I have 2 instead of 1? Because of the 2 here. Why do I have 2 here instead of 1? Because of the 2 here. Why do I have 2 here instead of 1? Because I multiplied the cocycle by 2 so that it takes values in z instead of half z, okay? So it's not really, not an essential thing, okay? Now let's look at this one bit longer, and if you don't mind, let's divide by t. And you will see that what do we really have here? If I take this point omega naught and launch a line of length t on the staircase, of course I make it wind around the staircase in accordance to all the identifications, but it's still a line. Okay, so let's call this line AT. Okay, so let AT be okay, phi beta t omega naught t between 0 and t. This is just a line, okay? It wraps around the surface, but it's a line. So basically what I'm calculating here is the intersection of this line with the rectangle with z coordinate 2 eta, and I measure the length. And by dividing by t, I'm dividing by the length of AT. Okay? So now we have a geometric presentation of the quantities we need to understand to analyze these histograms. And it is the intersection of a long line with a particular rectangle. Okay, so suppose this is rectangle eta, or 2 eta, then basically I need to calculate the ratio between this length and the total length. Okay? Now, it looks like I took something very, very explicit and simple and translated it into a very, very complicated geometric problem, because you have here a line that winds around the surface in a complicated way. But the point is that it's much easier to use a renormalization trick on the staircase than it is on the interval. So I have actually very effective ways of simplifying lines on the staircase. And let me explain to you what these methods are. So before I do this, I want to remind you that if you have an automorphism and you have a total automorphism which is hyperbolic, okay? and you take a line which is very, very long and winds around the torus in a very, very complicated way, but suppose this line is in the stable direction of the automorphism. If you apply the automorphism to it enough times, it will shorten. So from a very, very long line that winds around the torus, you will get a very, very short line, which is just a short line. It doesn't have any chance to wind, so it's simple. Okay, so this way you can simplify a very, very long line on the torus by applying a suitable automorphism. And that's exactly what we're going to do here. Okay, so here is the lemma that allows us to do this. So again, due to Pat Hooper, Pascal Hubert, and Barak Weiss, for every matrix in gamma 2, so what is gamma 2? Gamma 2 are all the matrices in SL2Z which have the parity conditions odd, odd, even, even. There exists a map, psi from the staircase to itself. So ST is going to be the staircase. That's the staircase. As follows. So first of all, it's going to be affine. Affine means constant derivative. So the derivative is going to be this constant matrix for all P inside the staircase except the corners. Think about the total automorphism, okay? 2 is going to be homogeneous. What does homogeneous mean? There is a natural symmetry on the staircase which has a derivative equal to the identity, but it's not the identity. It's the map that climbs up a stair. Okay? Let's call it D. So I can make my automorphism commute with it. Okay? And the third condition is zero drift. Zero drift means that 1 over n z coordinate psi a n p converges to 0 lebeg almost everywhere. So you choose a p at random, at rectangle 0, let's say, and you start applying the automorphism. Then you will move around like crazy on the staircase. But if the average change of the z coordinate is 0, almost everywhere, then I have zero drift. So it turns out that you can always construct such symmetries. Okay? And now, what's the game that we are going to play?
Omri?
Yes.
Could you indicate which direction z is in the picture?
Yes. So this is z equals 0. This is z equals 1. Yeah. Yeah. I'm tagging the stairs by integers.
So you get the integer coordinate of the state.
Yes. Yes. Exactly. Other questions? Okay, so now what's going to be this simplification procedure? So the renormalization idea is given T, find a matrix MT in SL2Z with these parity conditions such that MT, when you apply to the velocity, it contracts it, but not too much. Then psi, the automorphism with this matrix, when you apply it to AT, the orbit up to time t, will be will be a line segment of length approximately 1, but different direction, mt beta 1, maybe not the same direction, and different, maybe different, maybe it starts at a different rectangle. Start at z equals, let's call it zt star. Maybe a different place. So basically, the picture is as follows. I can use this one. Okay. I have another one. Yeah, that's right. I forgot. Okay, so the picture that I have in mind is this. I start from the staircase, and I start at rectangle 0. Okay? And I'm interested in how many times my orbit crosses this rectangle, okay? So I take my line. This is my initial condition. It starts at the top of rectangle 0, and then, you know, it does something. It's supposed to be parallel. So anyway, you understand. So I'm interested in the ratio of the intersection with this rectangle to the total length. My problem is that this object is complicated from the geometry point of view because there are lots and lots of windings. But if I manage to find this matrix MT, which shortens it, then what will happen when I apply my automorphism is that I will get perhaps another line, maybe different direction, but length which is bounded away from 0 and 1, so the length will be pre-compact, okay? Maybe it will start at a different height, okay? This is actually very, very important, this phenomenon of starting at a different height. So please remember this is going to be crucial at the last lecture, okay? So the idea is that whereas the original orbit is very difficult to understand, the image is very easy to understand because it doesn't have the chance to wind around, okay? Moreover, if I'm able to find a matrix so that the length is bounded by a constant over t, it will not degenerate, okay? So it will be a pre-compact family of intervals, and I can just imagine that it's a constant interval by passing to subsequences. I'm sorry.
By replacing the map by a constant one, you can always assume that you start at the same point.
That what is important?
Start at the same point. Right?
Okay, so the reality is that these points, I mean, there are only 4 different corners because of identifications. And the fact is that these automorphisms preserve these points. They extend continuously to the corners and preserve them. But the problem is that each point here is the meeting point of infinitely many sheets. So you have infinitely many lines with the same direction emanating from each corner. And what could happen is that you have this rotation. And this is not something that you should conjugate away because as we will see at the last lecture, what really determines the question whether the initial condition is generic or not, and generic for which measure, is going to be the growth properties of this quantity. So this is an essential feature of the argument, and it's not something that we can remove by assuming something without loss of generality. Okay, so this is the idea. That's the renormalization idea, and it's much easier to implement on the staircase because you have these automorphisms. You can probably do something like this on the interval as well, but it will be much more combinatorial and much less transparent. Okay, there is of course a question, can we find such a matrix? And let me explain why this is an issue. We are talking about integer matrices, okay? So except for finitely many integer matrices, all have large entries, at least one large entry, okay? And matrices with large entries like to expand, they don't like to contract. So there is a question, can we find a matrix like this? And this is exactly where the even continued fraction becomes handy, okay? Because it allows us to find such a matrix. So now let me tell you this fact. So this is the number theory fact. So how to find MT, okay? So I'll just tell you what it is. So I remind you that alpha is my initial angle, then I form 2 alpha minus 1. That also gives me the velocity vector on the staircase, and then I expand it into a continued fraction expansion, even continued fraction expansion. And now I'm going to write this matrix product. Maybe I should start it here. So that's upper triangular. Next one will be lower triangular. All the way until the end. Okay, each of these matrices is in gamma 2, and gamma 2 is a group, so this product is also in gamma 2. Okay, and the fact is that so if beta is of, sorry, alpha, it doesn't matter. If alpha is of bounded type, and beta is 2 alpha minus 1 is given by this even continued fraction expansion, then for every t, there exists n, which depends on t, which is basically log t, such that mn beta 1 is less than now where does bounded type become important? In the lower bound. I want to contract, but I don't want to contract too much because I don't want my image curve to degenerate. Okay, I want to keep it in a pre-compact family.
So you made the trajectory short by applying MT?
Yes.
Don't you make the number of boxes you hit very large in this? You're counting crosses between.
Okay, of course. I'm going to count something else. Let me get to that now. That's a perfect point. After all, what I'm interested in is that ratio. Okay? So let's see what happens to this ratio, or how to build this ratio from the short curve. That's a perfect comment, in fact. Okay, any questions on this so far? Yes?
If alpha is of bounded type, does that mean that the m's are bounded?
Okay, it means it's for even continued fraction expansions, the property of being bounded type is equivalent to the property that the digits are bounded, and that all the subwords of the form 2 minus 2, 2 minus 2, 2 minus 2 have bounded length. So they cannot, you can't find a substring in the continued fraction expansion of unbounded length of the form 2 minus 2, 2 minus 2, and so on. 2 minus 2, 2 minus 2 is the even continued fraction expansion of an integer, either 1 or minus 1, probably 1, I guess. Okay. We should do it. Okay. Okay, so let's address now the question of translating this into a quantity in terms of the renormalized renormalized curve. Okay. Okay, so I remind you that our automorphisms are affine. They have a constant derivative. Affine maps are similarity maps. They do not preserve lengths, but they preserve ratios of lengths. So the trick is to observe that what is important for us are not lengths, but ratios of lengths. And therefore, we are in good business. So if I look at this expression, so let's copy it here. At z to eta at, because psi t is affine, psi mt is affine, this is equal to the length of the image. Nothing to the ratio of the length of the image. Nothing changes. Okay? Affine maps preserve ratios of lines, ratios of lengths. So I can write this in the form AT star. AT star is, where is AT star? AT star is the image. Okay? So this is going to be phi mt z is to eta AT star. And I can think about this as the probability, I will write and then I will explain what I mean. The probability that psi mt inverse of q z is equal to eta, given that q belongs to AT star. And what I'm thinking now to myself is that I take a point on AT star which is random but uniform. Okay, so I choose a point randomly uniformly on my AT star. Okay, pick a point q randomly uniformly. I apply to it psi inverse. And I want to know what's the probability that I land at height to eta. Okay, so I pick a point randomly uniformly on the short segment. I apply psi inverse. Well, maybe it falls here, but maybe it falls here. I want to know what's the probability that it falls there. Okay? You understand what I mean? So again, this ratio of lengths is exactly the conditional probability of the event that psi inverse falls inside this rectangle when you sample the point randomly uniformly from this line segment. Okay, that's good. So now, let's start waving hands vigorously. So I have 10 minutes. Okay. What I'm aiming at is to rewrite this probability in the form of what's called the hitting probability of a random walk. And then, in the next lecture, we will discuss the problem of estimating these probabilities using a local limit theorem. That's where we are going. Okay? So, let me rewrite this in this form. Prob z psi mt minus 1 minus z is equal to, where's my, Okay, so this is supposed to be 2 eta. What is this? We are conditioning on AT. AT star is inside this rectangle, which has a fixed z coordinate. So this is going to be minus zt star. Okay? Now, this thing is what depends on the initial condition. This is where alpha and the initial condition 0, 0 enter the picture. That's the only part of this formula which depends on our initial condition. And we should expect that for some alphas, this will be generic for Lebesgue. For some other alphas, this should be generic for something else, and maybe not generic for anything. And therefore, the behaviors, the asymptotic behavior of these quantities will be so different so as to make the asymptotic behavior of the probabilities behave in a different way. Okay? So this is the most important part. This is the part that depends on the initial condition. That's what we need to understand. Okay, so I wrote it like this. Okay, basically because I said that the z coordinate is constant on AT star. Now, I want to do another trick. Where is my, I erased, okay, I'm not doing this very well. I erased the formula, okay. Here's another fact. So recall that MT is the product of many, many matrices, okay? 1 minus 2m to n minus 2m to n minus 1. Okay? So I'm going to write this product in the following way. So write n times n naught is the product of two little n matrices, where AI is going to be the product of n consecutive matrices. Okay, I have a product of, how many matrices do I have here? 2n. Okay, for each coordinate gives me two matrices. So I have 2n. So imagine that I take my 2n to be n times n naught. And I'm going to parse this long product of matrices as product of blocks of length n naught. Okay? Do you understand what I'm doing? I'm not explaining this very well. I'm going to bunch every n naught, every two n naught matrices I'm going to bunch. And I'm going to call these products AI. I'm not being clear, right? But I'm saying something very, 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 very simple. What?
Do we know what N0 is in advance? Or did you tell us what N0 is?
I'm going to tell you what it is now, okay? But given any N0, I can parse into blocks. And now here is the lemma. For some N naught, the sequence AI is uniformly hyperbolic. So what do I mean by this? So let ES0 be the span of beta 1, that's the direction of my flow. And let EU0 be the span of the vector which is orthogonal to it. And let ESUI be AI dot A2, A1, E0, SU. Okay, I'm defining directions. Okay, A0 maps the first pair of directions to the second one. Okay, you understand. I'm defining a sequence of directions. And then the statement is that this behaves like the stable and unstable direction of a hyperbolic cocycle. Then there exists lambda such that AI on ES I minus 1 has norm less than lambda, less than 1. AI minus 1 inverse EU I is less than lambda. So the stable one is contracted forward, the unstable one is contracted backward, and the angle between them is bounded away from 0. Okay, it's uniformly hyperbolic.
So here is where you use the bounded type.
Absolutely. That's yet another place where I'm using bounded type. Yes. Okay? So now I decompose the matrix, but I can also decompose the automorphism. So let's write our automorphism as the product of the associated automorphism which correspond to these matrices. Okay? So D Ci is AI. Okay? So now let's continue with this formula. And let me write it in this form. Telescopic sum. N Z Psi I inverse minus Z Psi I plus 1 Psi n minus 1 is equal to 2 eta minus ZT on AT star. I just wrote a telescopic sum. What's written here? Think about the following process. I have my staircase, and I have my target rectangle, 2 eta. This is the rectangle which appears when you try to understand the number of times the local discrepancy is equal to 2 eta. Okay? I'm picking a point randomly uniformly on some segment here. This rectangle is rectangle at another height. The height is ZT star. Okay? I want to know what's the probability that if I choose a point at random here, when I apply psi mt inverse, I land here, okay? But I can decompose my automorphism into the product of this uniformly hyperbolic sequence of automorphisms. So what my point will do when I break my automorphism into steps, it will perform a sort of random walk. Okay? You understand what I'm doing? Instead of applying my renormalizing automorphism at one step, I'm going to apply it at several steps. You understand what I'm doing? And then when I take my point, it will start moving around. These are chaotic maps. It will start moving around and perform a random walk. And what I'm telling you is that what I'm interested in is the scenario, the event, that the sum of the jumps due to each and every one of these automorphisms adds up to a fixed quantity. You understand what I'm saying? Should I repeat? I am interested in the probability that if I choose a point randomly uniformly on this segment, after applying the automorphism with this huge matrix, I end up at this rectangle. Now I'm going to break down my big automorphism into the composition of n small automorphisms. In fact, there are only boundedly many types of these automorphisms because these are blocks of length n0 and all the digits are bounded. Okay? So there are only finitely many types of these automorphisms. And I want to know what's the probability that the sum of the jumps due to the consecutive applications of these automorphisms add up to this. Okay, so now I'm going to wave my hands vigorously and tell you that using symbolic dynamics for non-stationary sequences of uniformly hyperbolic automorphisms, and I'm going to mention the names, put it here because I want people to see it, Arnoux and Fisher. And Adler-Weiss. So using the non-stationary version of Adler-Weiss due to Arnoux and Fisher, I can, that's overstating it, I can approximate this probability by probabilities of the form sum fi xi is equal to z and let's call it sharp because it's not exactly this, given xn is equal to xn, where xn is a Markov chain. Okay? Just like the measure of maximal entropy for a hyperbolic toral automorphism, when you code it by Markov partition is a Markov chain, the same happens here. Except that because we are not using the same automorphism, it's not a stationary Markov chain, it's an inhomogeneous Markov chain. Inhomogeneous Markov chain is a Markov chain such that the state spaces change in time and the transition probabilities change in time. Okay? So at this point you go to the library and you look for books for local limit theorems for inhomogeneous Markov chains, and you realize that you have to do it yourself. So how to do it? What is the local limit theorem for inhomogeneous Markov chains, we'll discuss in the last lecture. Okay.